My name is Gert Halooy. I'm from the German Aerospace Center in Munich. And this is Kees Vlaar. He's a graduate student from the TU Delft. And Kees has been working on a new control method in our institute. And we really would like to see this method, or controllers based on this method, see it fly on an aircraft. And the University of Minnesota, the UV lab, is offering a real nice opportunity to do such a thing at low cost, at low risk. So that's basically why we're here.
Yeah. And we make use of all the simulation models, and this gives us a way to prepare really well. While we are back in Germany, we could already do software in the loop test, send data using the real-time workshop to Minnesota, where they already performed hardware in the loop test. And this is a very successful method, since we already have good results even before we were already in Minnesota.
Yeah, so that's really a point that really helps a lot. So we are getting a lot of support in preparation of the flight test and doing the flight test. So it's really great to be here, to be working with the people here. So it's really nice.
Yeah, and in practice this means after you arrive, within a few days you can already go do some flight tests, and for us means we're going to do flight tests on the 4th day already. So that's really quick.
Yeah, the good thing is we are not testing so much advanced control functions or so. It's just a new method, and it's really, even though the aircraft is limited size, it's really representative. So if it works, we really can say, okay, it will work on bigger aircraft, and that's what we are very interested in.
Hi, my name is Paul Freeman, and I'm a PhD candidate in the Department of Aerospace Engineering and Mechanics. My research has been supported by this NSF grant. Some of the motivation for our research is that reliability certification is a major technical roadblock to integration of UAVs into the national airspace. We're researching analytical redundancy approaches to improving system reliability. We first began by looking at air data system faults, because this information is critical to guidance, navigation, and control tasks. Failures have been responsible for several accidents, and we want to improve the reliability of these systems. We began by modeling faults from physical first principles, and validated the models using experimental test data from faulted Goodrich air data probes. We used model-based robust filtering techniques and estimated the static and total pressure faults in these systems. We extended these robust filtering techniques to a study of control surface impairments and gyrosensor faults. We additionally developed simple data-driven anomaly detection algorithms, because we believe that dissimilarity and analytical redundancy will lead to better detection and isolation of faults. Recently, we've been working on comprehensive reliability analysis for our aircraft, using industry standard tools such as failure modes and effects analysis and fault tree analysis. We've extended these tools by choosing one fault, in this case, a stuck elevator, while allowing control surface reconfiguration, and performed a deeper study of the effects of that fault. We've been able to determine the achievable flight envelope and better understand controllability implications during reconfiguration. Adaptive control is often proposed as an analytical solution to the reliability problem, but it doesn't always take the physical system limitations into account. We are trying to take a step back and develop a fundamental understanding of the interaction between physics and these algorithms. We would like to use this understanding to develop reliability metrics which can help quantify the real system risk and make certification of these systems possible.
Hi, I'm Brian Taylor. I'm the director of the University of Minnesota's Uninhabited Aerial Vehicle Lab.
Often the most visible part of our research infrastructure are our aircraft, and we have two of them. First, there's IBIS, which is an Ultrastick 120. Next is Thor, which is an Ultrastick 25E, and it's about 60% of the size of IBIS. Both of these aircraft hold the Goldie flight control system, and I like to think of it as the bridge between the physical system, so the aircraft and what's going on in the environment, and the cyber system, so all of our navigation filters and control laws that are running.
This infrastructure allows us to quickly transition our research from concept through flight.